This section is somewhat short, and it kind of fits between all of our graphing sections. It's about the mean value theorem. Now, this is kind of similar to something we did before with the intermediate value theorem, and this is going to be one of those theorems that gets used a lot to prove things, but not necessarily a theorem that we're going to use directly very much, okay? So let's talk about, first we start with Rolle's theorem. Now Rolle's theorem is sort of the precursor to the mean value theorem, and it turns out that Rolle's theorem is actually a subcase of the mean value theorem. But usually what you do is you prove Rolle's theorem and then you use Rolle's theorem to prove the mean value theorem. And once you've done that, Rolle's theorem can kind of go away because the mean value theorem absorbs Rolle's theorem, okay, as being a more general case. What am I talking about? Well, let's go here. So, let f be a function that satisfies the three hypotheses. So, first of all, f is continuous on the closed interval a to b. Second, f is differentiable on the open interval a to b. And then the last thing is f of a is equal to f of b. Then the conclusion of the theorem is there is a number c in the interval a to b such that f prime of c is equal to 0. Now, what is this theorem saying? This theorem is saying this. Suppose I've got a point here at a, and a point here at b. They are the same height for this function. Now, the function is differentiable, which means the derivative exists over the entire interval, and the function is continuous over the entire interval. And so what I have to do is do this, okay? I can go up, I can go down, all that kind of stuff, but I have to return to the same height, and because it is differentiable, there's no sort of spikes or cusps or anything like that. It's continuous, so I don't have any jumps or asymptotes. And the theorem says that in the interval somewhere, there's going to be a place where the derivative is 0. Okay, and the one I drew just has 4 of them, but you're guaranteed 1, right? If it goes up and comes down, you get 1. So that's what Rolle's theorem says. If you go up, you come down, you reach a max somewhere in the middle, provided that you start and stop at the same height. Okay? Now, this is kind of like the intermediate value theorem in that this says that there is one, but it has nothing to do with how to find it. The theorem is not constructive. It is merely one of those existence type deals, and so we have no idea where it is. Okay? Now, the mean value theorem is going to be very similar to this. The mean value theorem has 2 hypotheses instead of 1, and they are simply the first 2 hypotheses from Rolle's theorem. So f is continuous on a to b, and f is differentiable on open AB. Then there is a number c in the interval a to b such that, okay, so before it was f prime of c equals 0. Here it's f prime of c equals f of b minus f of a over b minus a. Now, what is going on here? Well, let's just talk about what Rolle's theorem does. So Rolle's theorem says this. If I start here and end here and I go up and down, then I'm guaranteed a place in the middle where the derivative is 0. So here's my a, here's my b. Now, I can do this pretty easily. Here is Rolle's theorem. That was Rolle's theorem. Here's the mean value theorem. Mean value theorem is just this tilted like that, because this thing right here is the average rate of change on AB, and so it's the slope of the secant line between f of a and f of b, and this theorem says it guarantees you that the slope is the same as the average slope somewhere in the middle. Okay, so just like the slope was 0 here and 0 here, now that slope matches the slope of the secant line. Okay, and this actually looks better on the iPad than it does on the board because I can do that kind of turny thing. But that is what the mean value theorem says. Now let's talk about how the mean value theorem sort of absorbs Rolle's theorem. Well, if f of a equals f of b, then this is 0, and you get f prime of c equals 0. So the mean value theorem doesn't need to be a standalone theorem anymore. It's a standalone theorem because it is traditionally used to prove the mean value theorem. Okay, and it's good to know too, right? When we're looking for maxes and mins. This one down here, although you can kind of scratch it because now you can just apply the mean value theorem. If that case number 3 happens, then this equals 0, and you have Rolle's theorem, okay? Now, this section pretty much has a couple of applications, but generally the homework problems all look the same. So let's start here, which is kind of what's happening. Suppose that you drive from Chowchilla, from Fresno City to Chowchilla in 30 minutes, okay? And when you get there, a police officer gives you a ticket for going 80 miles per hour somewhere on Highway 99. Is that fair? Okay, well, do you like it? No, but is it fair? So what is happening here? So let's see. We go 40 miles in 30 minutes, okay? So somehow we know when we left and when we arrived, however they would know that. What would happen? What's my miles per hour? Okay, well, my average miles per hour is going to be, let's call it time 0, t equals 0, leave, and t equals, I need to go hours, right? So t equals 1/2, arrive. And then f of 0, that'll be my position. My f of 0 is 0, and then f of 1/2 is 40, right? Okay, so what I'm saying is at time 0, we haven't left. At time 1/2 hour, we've driven 40 miles. So then what is the average rate of change here? And the mean value theorem will say that we had the derivative, f prime of c equals f of 1/2 minus f of 0 divided by 1/2 minus 0. So that gives me 40 miles minus 0 divided by 1/2, which is, 40 divided by 1/2 is 80. So let's see. The mean value theorem says the derivative at some point between here and Chowchilla, the derivative is 80, meaning if f is our position function, our velocity, and speed in this case, was 80 miles per hour somewhere between here and Chowchilla, meaning this is totally reasonable. Now, this is a made-up example. However, this is actually a real thing. So when you drive down the road, you can see these things that say patrolled by aircraft. Well, what happens is there's these like markers, okay? And these markers in the road are all 1 mile apart, right? And so what they do is they time you from one to the next, and they can time you between them. And if you get there too quick, then they can give you a ticket for going over the speed limit. So this kind of thing actually is used, but not quite in this situation, more in this situation. And I almost always ask students if you've ever gotten a ticket like this. And only once did I have a student say yes. They got a ticket for via this method for driving too fast near an airport. So anyway, watch out for that. So this is a real thing, even though this example is probably unlikely to happen. Now, I have a couple more examples here, and this is what kind of the general homework problems for this section look like, okay? So, hey, here's a function, find the values of c that satisfies the conclusion of the mean value theorem on some interval, okay? Like, this is exactly what the problems look like, and mostly we have to do, all of our sort of algebra work will be after using the theorem. That will just kind of be a bunch of algebra stuff, but let's give this a go. So on the interval, it says that f prime of c is going to equal f of 2 minus f of negative 1 divided by 2 minus negative 1. And so I need to plug some stuff in here. That is fun. So let's see. 2 times 2 cubed. So we're doing f of 2, right? Plus 3 times 2 squared minus 12 times 2. That's 4. And then I need -1. So it's going to be -2 plus 3 plus 12 gives me 13 over 3. Whoops. Clear. Okay, 4 minus 13 is -9 over 3 is -3. All right, so what I want to do is I need to figure out where does the derivative equal -3. Well, f prime of x is 6x squared plus 6x minus 12. And I need to solve f prime of x is equal to -3. So that's what we're going to do. We're going to do 6x squared plus 6x minus 12 equals -3 and start solving. Add 3 to both sides. Factor out the 3. And let's hope that this factors does it. Let's see, 2, 6. I don't think it does. So x is going to be -b plus or minus square root b squared minus 4 times a times c all over 2 times a. -2 plus or minus b squared was 4, so I get, what's that? 4 minus 4 times 2, -3, 28. That does reduce. However, something I can't just stop here because what the theorem says is that there's a solution guaranteed in this interval. And so what I need to figure out is which one of those two is in that interval. Now, they could both be in that interval, or they could, or only one of them, okay? These are the only possible solutions, so I know that one of them has to be. So I'm going to plug them both in. I need to figure out which one. I need to sort of estimate these and figure out which one's in this interval. Now, what I hope is that the first one I try fails, because then I don't have to check the second one, because the first one failed and I'm guaranteed to have one. The second one is guaranteed to work. If I try the first one and it works, then I have to try the second one because you are allowed to have two, okay? So that's kind of a bummer. I think the negative one is not going to work, so let's do -2 minus the square root of 28 divided by 4. -1.8. Okay, so the negative one does not work. So -2 minus root 28 over 4 doesn't work. And so x equals -2 plus root 28 over 4 is the only solution here. Okay, the only one in the interval -1 to 2 that is the only c that satisfies the mean value theorem for this function on this interval. Okay, again, if I tried this one first and it worked, I'd also have to try this one because there could be more than one c. All right? Very good. Let's try another one here. So suppose that f is a continuous function with f of 2 equals 3 and f prime of x is less than or equal to 5 for all x. What is the maximum value of f of x of f of 6? Now, there's a fancy way to do this and a not fancy way. Let me do the fancy way first, just to get it out of the way, and then we'll talk about the not fancy way. All right. So the fancy way is to say is to use the mean value theorem here. Okay. So is to say that f of 6 minus f of 2 over 6 minus 2. Okay, so f of 6 minus 3 over 4. All of this is always less than or equal to 5, okay? Because the derivative, whatever this value is, the derivative will be equal to that somewhere in the interval. And so since I know that the derivative is always less than or equal to 5, here I go with this thing here. And so I know that f f of 6 minus 3 is less than or equal to 20, and so f of 6 is less than or equal to 23. Okay, so there is the fancy mean value theorem way to do this. But there's an easier way just to kind of think about it, and that is if at 2 I'm at 3, okay, I want to know 1, 2, 3, 4, 3, 4, 5, 6. As I move over 1, 2, 3, 4, what is the highest we can be? And let's start at 3, right, not 2. What is the highest that we can be up here? Well, if the slope is always less than or equal to 5, it will obviously be the most when when the derivative is equal to 5, which means every time I go over 1, I go up 5. Okay, so I'm going to go over 1, up 5, over 1, up 5, over 1, up 5. Let's see, 1, 2, 3, 4. Got it moved over here. Okay, so what is that? Well, I went over 4, and each of those I went up 5, which is 20. 20 up from where I started, which is 3, so the max is 23. Okay, that is the much better way of thinking about it. But these problems are officially in this section because we can use the mean value theorem on them. Okay, but definitely think about it in this way. All right? Okay. Theorem 4.2.3, a couple of things to wrap up in this section before we move on to how graphs are affected by the derivative. So if f prime equals 0 on an interval, then f is a constant on the interval, okay? Now, the reason this is because of this. So suppose that we have C and D in the interval. Suppose that we have 2 points C and D in the interval AB, right? Okay, then what I know is that f of C minus f of D over C minus D, I can use the mean value theorem, and so f prime of some point in the middle is going to equal this. Now, what I know is that this thing is equal to 0, so the mean value theorem is equal to 0, like this, for everything in the middle. Well, what I have then is I can multiply both sides, and I get f of C minus f of D is equal to 0. And so f of C is equal to f of D, okay, for any points inside the interval AB. So if any 2 points, C and D, are inside the interval AB, they're all equal, and I can start all of this at A and end all of this at B, which means that f of x is constant on the interval AB. Okay, last theorem. So if a derivative is 0, the function is constant, and this one's going to be something important to use around here. Here it says, if f prime equals g prime for all x in the interval a minus b, then f minus g is constant. That is, we have f is equal to g plus c, where c is some constant. Okay? All right, well, what do I need to know? I know that their derivatives are equal. So here we're going to say that some new function h of x is equal to f of x minus g of x. Then h prime is f prime minus g prime. And by assumption, those two things are equal, and so h prime is equal to 0. By the previous theorem, I know that it means that h is constant. So h of x is equal to some constant c. And what is h of x? Well, it means that f of x minus g of x equals constant. Okay, so that means I have the first part here. F minus g is constant. There we go. That first part is done. And that really means that f of x is equal to g of x plus some constant. Okay, so if we have two things whose derivatives are the same, it means they differ by a constant. And this kind of makes sense going back and thinking about it. If you have a function like f being, x squared plus 3, and another function g of x being x squared plus 5, what is the derivative of those? Well, the constants go away, and you both get 2x for both of them, which means they differed by only a constant. There is this kind of feeling that if we have functions whose derivatives are equal, then the functions are equal, and that's not true. But it is true that they differ by only a constant, and we're going to use that in later sections. Okay, that is the end of section 4.2. In the next section, we'll talk about derivatives and graphs. I will see you then.